For the next several videos, I have the privilege of talking to you about vectors, which is one of my favorite mathematical topics. Vectors are incredibly important in both mathematics and physics, as well as in computer science, for representation of really common everyday stuff. By the end of today, we should be able to state what the definition of a vector is, list a couple of real-world quantities that can be represented by vectors, and graph vectors, represent them visually on the xy plane. Now before I define a vector, for contrast I want to define what's called a scalar. And a scalar is just a single number, a quantity that can be represented by a single real value. Some common examples would be the weight or the mass of an object. The weight or the mass of an object is communicated by a single number, 20 kilograms, 100 pounds, for example. The cost of an object is represented by a single number, $5, 1,000 euros, that kind of thing. Temperature, height, population, these are all quantities expressed by a single number. Now vectors, by contrast, are real-world quantities where a single number is not enough to describe what's going on. A vector is a quantity that must be described using both a number and a direction. For examples of some quantities that are represented by vectors, we have movement, which is also known in physics as displacement. When you're describing the movement of a person or an object, this is described using both a number and a direction. The direction in this case is the direction of movement. Which way are they traveling? And the number is used to communicate how far they are traveling. If I was describing the movement of an object or of a person, it would not be unusual for me to say something like 20 miles southeast. The 20 miles is the number communicating how far the movement was, and southeast was the direction communicating the direction of movement. Now similarly, velocities are something that are usually represented by vectors. For a velocity, we communicate both the direction of movement and in this case the number is telling you how fast the object is moving. To describe a velocity, it would not be unusual for me to say something like 50 miles per hour to the south or to the north. The 50 miles per hour is the number representing the speed, and north is the information about the direction of the movement. The third quantity that is more correctly expressed using vectors would be forces. In this case, the direction would tell you the direction in which the force is being applied. And the number, in the case of a force, is what is communicating to you how strong the force is. The strength, or what is more commonly called in physics, the magnitude of the force. So it would not be unusual for me to see something like this when a force was being communicated. A force, for example, of 30 pounds applied downward. This, for example, would be an appropriate expression of the gravitational force which is imposed on a 30-pound object. Gravity pulls you downward, and the size of the force is equal to the object's weight. Now, as you can probably already imagine from these few examples, vectors are probably extremely important in physics, because what is physics about fundamentally? It's about movement and it's about forces, right? Vectors are also extremely important in computer science, for reasons that will become more clear if you end up taking linear algebra, what we call here Math 240. Now, just like individual numbers can be represented on a number line, there is also a way to visually represent vectors. Vectors are represented visually as arrows. And when you're drawing an arrow that represents a vector, the following two principles apply. The length of the arrow that you draw should be a match to the number that's being communicated by the vector. And the direction of the arrow that you draw should be a match to the direction of the vector. Now, traditionally, when we're drawing these arrows, the most common practice is to draw them in the XY plane. And the most traditional practice is to draw the arrow so that the tail of the arrow is at the origin. But this is not, strictly speaking, required. It's traditional. This is the most common and conventional practice. But it's just as possible to draw your arrow anywhere in two-dimensional space with its tail at any location. A vector is composed just of its length, the number, and its direction. So the actual starting position doesn't affect what vector you're working with. It's just a matter of tradition to draw it with its tail starting at the origin. For an example, let's draw some of the following vectors. For example, a vector with a length where the number is equal to 2 units and the direction is the one that corresponds to an angle of 45 degrees. So following tradition, my choice will be to draw this vector in the XY plane so that the tail end of the arrow is at the origin. And I'm going to draw the vector so that its length is equal to 2 units. And so that the angle that it forms with the positive x-axis is equal to 45 degrees. So the vector in this problem would be the one in blue, 2 units long, pointing from the origin into a direction corresponding to 45 degrees. Let's draw an arrow corresponding to the following vector. This is the vector that represents a force being applied downward that has a magnitude of 10 units. So, following tradition, I'm going to sketch this on the XY plane, and the vector I'm going to position so that its tail is at the origin. And then I'm going to extend the vector 10 units down. Apply downward, so the vector is pointing straight downward. A magnitude of 10 units, so the length of this arrow is intended to be 10 to reflect that. What about the vector representing displacement from 1, 3 to 4, 0? Now, this is a situation where I might be inclined to take advantage of the fact that it is not mandatory to draw your vector with the tail end at the origin. Instead, I think what I'll do is I will plot the two different positions, 1, 3 and 4, 0. And I'm just going to draw the arrow that stretches from the initial position toward the final position. This yellow arrow would be the vector representing this movement, this displacement. Finally, let's draw an arrow which represents a wind which is blowing southeast at 5 miles per hour. Because they're describing to me the direction of the wind and the speed of the wind, the vector in this case that combines these two pieces of data would be the wind's velocity. to employ the physics language. So using the traditional convention that positive x is east and positive y is north, and following the tradition of drawing the arrow with its tail at the origin, I'm going to extend an arrow to the southeast, and I'm going to make that arrow 5 units long, and this will communicate a velocity of speed 5 miles per hour, direction southeast. Now, although it's possible to represent vectors visually, it can be a lot more convenient and compact to represent vectors using symbols instead of drawings. And when we represent vectors symbolically, we use notation that looks like this. 2 numbers separated by commas, almost like a point or an interval. But the big difference is that the a and b in this expression are surrounded by angular brackets. The angular brackets are the symbol that you're looking at a vector. Now, what vector are you talking about if you write down angle bracket a comma b angle bracket? You're talking about the vector which satisfies the following property. This is the vector which represents displacement / movement from the origin at 0, 0 to the point a comma b. To rephrase this, this is the vector which, if drawn, according to tradition, with its tail at the origin, the arrowhead, the tip of the arrow, would be at the location parenthesis a comma b. And the numbers a comma b here are called the components of the vector. Components. So let's take a couple of vectors which are being described symbolically, a few vectors which are being described using components, and let's represent them visually. Let's see what they look like in terms of a picture. To draw, for example, the vector angle bracket 3 comma 2, I would start on the xy plane and I would position the tail of the vector at 0, 0. Then I would draw a vector so that its arrowhead lives at the location 3 comma 2. The vector is the quantity that stretches from 0, 0 to the location parenthesis 3 comma 2. Likewise, if I wanted to draw -4 comma 0, well, I wonder why this numbering keeps getting messed up. Oh well, if I wanted to draw 4 comma 0, I would draw the xy axes, and I would start by positioning the tail of the arrow at the origin as per tradition, and then I would draw the arrow so that its arrowhead was located at the point -4, 0. The point with parenthesis is this location on the far left, and the vector is how we reach that location from the origin. And for one final quick exercise here, we have the vector 1 comma 4. So starting at the origin, we'll go 1 unit over and 4 units up, and this arrow is the vector 1 comma 4. Now let's try and go backward. Let's try and take those vectors that we drew 2 exercises ago, and let's try and figure out how that same vector would be represented symbolically. Now hold on for just a minute. I'm going to go steal our graphs from the previous exercise so that we can reference them here. So I've gone and grabbed the drawings from the previous exercise. And for the sake of my exposition, for the sake of the explanation, I think I'm going to tackle these questions slightly out of order. Beginning with the second exercise, where we had the force of magnitude 10 applied straight down. When they want us to express these vectors in component form, what they're essentially asking for is, if I drew this vector where its tail was at the origin, where would the arrowhead be? Now in the second exercise, the arrowhead is relatively easy to locate. The arrowhead is 10 units directly downward, so the x and y coordinates would be equal to 0 x's and negative 10 y's. What, therefore, would be the component form, the symbolic representation of this vector? The symbolic representation would be angle bracket 0, comma, negative 10. That would be the symbolic representation of this vector, the symbolic representation of this force, 10 units of magnitude applied straight downward. Now, for the sake of exposition, I will return to my first example. In this case, we have a vector with a length of 2 units and a direction corresponding to an angle of 45 degrees. To find the components of this vector, we basically just have to figure out if we drew this vector with its tail at the origin, which we have already done, where would the arrowhead end up? The location of the arrowhead, when the vector is drawn starting from the origin, is what's going to give us the components of the vector, the a and the b. Now, this picture probably looks a little bit similar to some of the stuff that we were working on when we did polar coordinates. The location here described in green in polar coordinates would just have an r value of 2 and a theta of 45 degrees. And what we're basically just trying to figure out is what the horizontal and vertical components of this location would be, the x and the y. So I can just use those formulas from yesterday to help me to convert polar coordinates into Cartesian coordinates. The x component, the horizontal component of this vector, can be found by taking 2 times cosine of 45 degrees. And the y component can be found by taking 2 times sine of 45 degrees. So that would be equal to square root 2, and this would be the component form of the vector, which is drawn here, the vector of length 2 units with a direction of 45 degrees. Similarly, skipping down to number 4, this vector has a magnitude, a length of 5, and what would its direction angle be? For southeast, we would also be going at a 45-degree angle, but this time we would be turning clockwise from the positive x-axis. So where would the arrowhead be? I could find the x component of the arrowhead by taking the length of the vector, 5, and multiplying it by cosine of the direction angle. And to find the y component of the vector, we can do the same thing except with sine. This would be equal to the components 5 times root 2 over 2 and negative 5 times root 2 over 2. This would be how we would symbolically represent the vector here, which is in turn representing the velocity of this wind. Now for our final example, I'm going to jump back to number 3. I'm leaving this one for last because fundamentally it's rather different from the other 2 examples. This was the only case where we, for our convenience in the previous exercise, decided not to draw the vector with its tail at the origin. This point is located with its tail at 1, 3, the initial position in our movement. In order to find the components of this vector, we're going to have to imagine shifting the vector so that its tail is at 0, 0 and not at 1, 3. But we're going to have to be careful to make sure that we shift the arrow without changing its length or its direction. Now, in order to move the vector without changing its length or direction at all, I like to take the following approach. I like to break down the vector that I drew into its horizontal and vertical pieces. For example, I would say to myself, okay, I have moved from the position where x is equal to 1 over to this position where x is equal to 4. When I did that, I moved 3 units in the positive x direction. I have also moved 3 units in the negative y direction to move from 3 down towards 0. So to recreate the arrow, I am going to start at 0, 0, go 3 units to the positive x direction, and the same 3 units in the negative y direction. So here is my newly shifted arrow, which also has 3 units to the positive x direction and negative 3 units in the y direction. So where is the location of the arrowhead now? The location of the arrowhead is 3 units toward positive x and 3 units toward negative y. So this is the true value of a and b, and therefore the vector in this problem would be angle bracket positive 3, angle bracket negative 3. This is the symbolic representation for the arrow in this picture. Angle bracket means vector. That concludes today's material. Today we defined what a vector was. A vector is a number and a direction, as opposed to a scalar, which is just a number. As scalars could be used to represent weights and masses, temperatures and costs, vectors can be used to represent movement, velocity, and force. Vectors can be represented pictorially using arrows. Although those arrows don't have to be drawn starting from the origin is the most traditional way to draw a vector. And the upshot of drawing a vector at the origin is that it allows you to see relatively easily how to write the vector symbolically in components. To write a vector symbolically in components, draw the vector starting from the origin and look at the location of the arrowhead. The location of the arrowhead is what tells you the component form of the vector.